I wonder how this problem went for you. Let's go through it. The events we're interested in are first, probability of no heads. So that's the event containing only tails, tails, tails. Now there are 8 outcomes in the sample space. The number of outcomes in this event, of course, is 1. So the probability of this event is 1/8. Next, we're interested in the event 1 head. That contains outcomes heads, tails, 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 heads, tails, and tails, tails, heads. So clearly the number of items now is 3, which means the probability of this event is 3/8. Then we're interested in having 2 heads. That contains the outcomes heads, heads, tails, heads, tails, heads, and tails, heads, heads. Again, we have an event with 3 outcomes. So again, the probability of that event is 3/8. And last, we're interested in the probability of getting 3 heads, which only has the outcome HHH. So N of E is 1. And the probability of E is 1/8. That's all the work we need to do to make our probability distribution. So again, what's going on here is, in part A, we were thinking more of descriptions and descriptive outcomes. Now we're letting a random variable do some counting for us. And what this particular random variable is counting is number of heads. The possibilities are 0 heads, 1 heads, 2 heads, or 3 heads. And we've computed those probabilities as 1/8, 3/8, 3/8, and 1/8. And bravo if you added those up to double check that they add up to 1, which they do because they add up to 8/8. Then our probability histogram will look like this. Now let's suppose we toss a coin 3 times, note the number of heads, then we perform that experiment again. In other words, we toss our coin 3 times again and note the number of heads. And we do this over and over and over. We'd like to be able to calculate what the average number of heads will be. And we'd also like to be able to know the standard deviation of that number of heads. There's a formula for this that tells us how to get the average number of heads. In fact, how to get the average of any random variable x. And that is, we take the individual x values, we multiply each one by its probability, and then we add up those numbers. For the standard deviation, we have to know the mean first, and what we do is we take the difference between each x value and the mean, we square that difference, then we multiply that square by the probability of the x value, we add all those up, and the last thing we do is take the square root of all that. By the way, you do not have to memorize these formulas. So let's see if we can apply that to tossing a coin 3 times and doing the triple coin toss over and over and over. Let's see what we should expect the average number of heads to be. We've already computed that the probabilities are 1/8, 3/8, 3/8, and 1/8. Now this is a complicated computation, so we're going to use a table to organize all the steps that we're doing. By the way, yes, you can find an online calculator that will do this for you, but there will be at least one problem on the test where I will give you a table and ask you to fill in the table. So I want you to understand what's going on here and know the procedure, even though you don't always have to go through this entire procedure every time you want a mean or a standard deviation. So again, we're going to multiply each probability by the value of the random variable. That's the x times p of x thing that we have up here. So I'll have then 1 times 3/8, 2 times 3/8, and 3 times 1/8. So let's see, that gives me 0, 3/8, 6/8, and 3/8. And then after we have those numbers, we have to add them up. That's this sign up in the formula. You may recall that was the Greek letter sigma, sigma being a Greek S. So if we add those up, we have 12/8. And I'm going to go ahead and simplify that to 3/2, which is, of course, the same thing as 1.5. Next, we're going to compute the standard deviation. Remember, standard deviation tells you how spread out the data is, how dispersed it is. In other words, how much variation there is between the different data values. For that, I'm going to take each x value, subtract the mean, square what I get, and then multiply that by the probability of that x value. So I have 0 minus 1.5 squared times 1/8. Then I'm going to have 1 minus 1.5, square that and multiply by 3/8. 2 minus 1.5, square that, multiply by 3/8. And 3 minus 1.5, square that, multiply by 1/8. And of course you're going to do all that on a calculator. You know, you might want to pause the video right now and do these computations on your calculator, just so that you can sort of check your calculator work and see that you're getting the same answers I do on these. I get 0.28125 for the first one. I get 0.09375 for the second one. I also get 0.09375 for the next one. And for the last one, I get 0.28125. Now I have to add those up, which gives me 0.75. Now don't forget, we haven't done the square rooting yet. And a common mistake I find people do is they don't write the square root down and then they forget that they're supposed to do it. And since they didn't write it down, I can't give them partial credit for having the correct formula. So let's put the square root in. That way we know we have to square root this thing. And our final answer then is sigma equals 0.866, and now I have rounded off. There's no reason to keep all those many decimal places in our final answer. A quick note, notice that the mean mu does not have to be one of the values of the variable. We got 1.5, which is not one of the x values. That's okay. That's just telling us that if we did this experiment over and over and over, and we took the average of our x values, we would get about 1.5.